Okay, hello everybody. I believe we are live. That's weird. This is weird. Something's wrong. I'm just trying to make sure that we're live on YouTube properly. Great. Okay, excellent. Hello everybody. Welcome back to the 9th part of this Golang tutorial series, Neural Networks from Scratch in Golang. There you go. That was a loaded thing. Brief intro and I don't know what I'm blanking on the word, but let's give us some context. This is the 9th part of going through neural networks from scratch in Python. It's a book that is all about going through neural networks from scratch in Python, but we are going through it in Golang, and this is the 9th part of that series. If you want to check out some previous parts, there's a link to the place in the description. Additionally, we're following along with a book, NNFS in Python, Neural Networks from Scratch in Python. A link to the book will be in the description as well. You could go to nnfs.io to check it out. nnfs.io, not this site. That's weird. I don't know what this is. nnfs.io. Okay, I'm messing this up. nnfs.io. Come on, people. Thank you. Here's the site. You could get the book, ebook, paperback, excellent book, highly recommend, especially if you're into coding in Python, but I figured it would be nice to do this in Golang. So, in the last video we talked about activation functions, specifically we talked about ReLU, rectified linear, the rectified linear activation function, because that is the most common activation function used when you're doing your hidden layers in Golang, in machine learning. So if you remember correctly, in the activations file that we have over here, we have this struct activation ReLU, which has one field, it's just output. Additionally, it has a function called forward. This is a forward pass. And all it does is compare each value in the output, or the inputs, which you put in here. If the value is greater than 0, it keeps it. If it's less than a 0 or equal to 0, it makes it 0. So, and there you go. So that is the ReLU. In this one, we're going to talk about another activation function called the SoftMax activation function. Now here we have a massive paragraph, which I'm going to try to sum up in the best words I can. So why do we want the SoftMax activation function instead of the rectified linear activation function? Well, we are going to be using the SoftMax activation function in the final layer of our neural network. So that's its point, that's its purpose. It's not supposed to be used in the hidden layers, it's supposed to be used in the final layers, but only for classification problems. So if you remember, our data that we have over here, it's pretty great actually that I have the image, the PNG that I can always refer back to and I don't have to always run it again. It's a spiral with 3 classes. And the point of our neural network will be to take in an input, basically being an XY coordinate on this plane, and it will tell you whether or not it should be in the red class, the green class, or the blue class. So that's its point, and so it's a classification problem. Now why is this important? Well, when a neural network gives back its outputs, it will give back probably 3 outputs, one for each class, and they could be in any range. They could be -600, 1000, and 23. Now, one way of interpreting that is it thinks that the second class, the 1000, is, so here, let's actually write this down. This is going to be known. Good. So one way of interpreting that is it thinks that the 1000 being the second class is the appropriate class for the point. So let's say output. Imagine the output looked something like this. Let's say -60, 23, and 2000. So clearly, it's thinking that it's the third class. That's one way of interpreting it. But wouldn't it be nice if we had the output in a form something like this? Output equals, let's say, 0.5. Actually, let's make this more appropriate to what this is. So this would be 0.001 basically. These are just, I'm trying to just sort of figure it out, but honestly, these are not ideal. And then this one would be like 0.99. So, although this is not going to work, I think. 0.1, and then this could be 0.8, and then this I guess could be 0.15, and then this one could be 0.05. So great. So this would be nice because these are all percentages. And otherwise, in other words, if you sum all of these up, you'll get 1. So the sum of all this is 1, I believe, right? Yeah, the sum of all this is 1. So that is basically what the SoftMax activation function is doing. It's basically putting it into percentages of the confidence of the neural network as to which class this given input is going to be. So clearly the confidence is highest for the third value, right? And so it would say that this, actually I'll make this bigger. Clearly confidence is higher for the third value, and so the neural network is basically saying, I think that the input, whatever it was, should be the third class. Okay, so there's a few things that we're going to need to do off the bat that you could figure out just based on what this is doing. First of all negatives are going to go, because having a negative probability kind of doesn't make sense. Additionally, we're going to normalize all these things. So we're going to find, so one great way of normalizing is you get the sum of all of these values and divide each individual value by that total sum, and that's a great way of normalizing things. The problem with doing that just straight off the bat would be that we'd be left with negative numbers, and we don't want negative numbers. We want only positive numbers in percentage form, and so that is what the SoftMax activation function does, really. What does it do? So this is the equation for the SoftMax activation function. What does this mean? It's e to the z at index I comma. It's a bunch of messed up things. It's anybody without a math degree won't really be able to make heads or tails out of that, and I'm sure maybe some of you are able to read that and understand it, but for those of us who don't, and we are simply coders and programmers, it may be helpful for us to look at it in code. So let's take a look at exactly what the SoftMax activation function does in code, and hopefully that will make things a little clearer. So if you remember correctly, in the main function, we had these two, we had the dense one and the activation one, and we passed through x to the dense one, and then we passed through the dense one's output to activation one, and then we printed out. We're not going to be doing any of that for now. We're just going to comment all of this out, and underscore, comma, underscore equals dense one, comma, activation one. It's a great way to simply var, I put a dot here when it should have been a comma, great. And we still want FMT, so let's just, for now, so that FMT doesn't go away, let's uncomment that, so we have that. Okay, great. Now let's take a look at the SoftMax activation function in code. So the first thing he's going to do is he's going to create, like, let's say that these were the outputs to a given neural network. So let's say outputs, colon equals float 64, and this is going to be a slice of float 64, and this will have the values, and I get to copy and paste the values because I have the book. If you want to do this, you should buy the book, and you should buy the book anyway because it's a great book. Hashtag not sponsored, but anyway, you should buy the book. Great, so these are the outputs. The first step for us is to exponent the outputs. Exponentiate the outputs. We do this with Euler's number e, which is roughly 2 point blah, 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 and referred to as the exponential growth number. Exponentiating is taking this constant to the power of the given parameter. So that is this step over here. We're going to go to each value, and we're gonna raise e to that value, and that will exponent all of our values. And this is the graph of y equals e to the x. So basically, for example, this is 4.8. So after exponentiating 4.8, so 1, 2, 3, 4.8, you end up over here. It's going to be a big number. So we're going to raise e to that value, and that will be our exponentiated values. So let's come over here, and this is a great way to do it in Golang. We'll say xvals colon equals make a slice of float 64 with a size of the length of outputs. Great, and now we could loop through for I, comma, val, colon equals range of range, and there's no, okay, Hannah, can you please spell? Range, there we go, of outputs. Exp vals index I equals math.pow, and you're going to have to import math up here. Math.pow, we're raising math.e to val. Great. And then, okay, great. So that will raise all of them to that value. And then he prints it out. So let's print that out as well. fmt.println exp vals. So one great thing about doing this, which I'm sure he will explain. So let's make sure these are the same. Yeah, 1 to 1 point, a lot of decimals. Yeah, these all look to be pretty good. Okay. Now, one great way of doing this is it gets rid of negatives. As you see, e to the x always approaches 0 as you go to negative infinity, but it never actually gets to 0. And things just become very, very positive. So this gets rid of all our negatives. It just brings everything to positives. Now, there are many functions that get rid of all your negatives. For example, x squared. Why don't we use x squared? This should be obvious, but if it's not, let me demonstrate. If you have these values, imagine you're trying to do a classification between two classes, negative and two classes. Let's just say two classes, and the program spits out -4 and 4. If the first thing you do is raise everything to the power of 2, then you'll end up with 16 and 16. In other words, the AI is not at all sure which one this is. But of course, that's not true. It was sure. It's just a negative number squared is the same thing as a positive number squared, and so we lose information when you just raise it to the power of 2, as opposed to e to the x, which you keep all the information, all the negative numbers, as you go to negative infinity along the x-axis, you also go towards 0 along the y-axis, and so you keep all of your information there, which is why we do exponentiation. Okay, great. The exponential function is a monotonic function. This means with higher input value. Yeah, so that he's just saying exactly what I said. Once we've exponented, okay, so now that we've raised everything now that we've raised e to all of those values so that we get rid of negative numbers, that was the goal. The reason why we did this is to get rid of all the negative values. The next thing we're going to do is we're going to normalize everything. How do you normalize things? Well, normalization means you want to take every value and put them between a range of 0 and 1, such that when you add up all the values, you get 1. As I demonstrated before, if you have, like, let's say, I don't know, 0.5, 0.25, and 0.25, this is normalized, because they're all between a range of 0 and 1, and they all add up to 1, so that's a great way of showing percentage. The best way to do this is to add up all these values to add up all the exponentiated values to get the sum, as he's doing over here, to get the base. This is called the normalization base, apparently. So, and that is what this is. This is the summation of all the exponentiated values to get the normalized base. And then, as you can imagine, we'll divide every single value by that normalized base. So the way to do this is, for now, we'll say norm base, which will be a float 64, I forgot the T, var norm, and then that's not how you spell base. I'm doing a great job here. Var norm base equals 0. And then as we loop through, we'll say norm base plus equals x vals index I. Great. In fact, we don't even need to do equals 0 because it will just initialize to 0. So norm base plus equals x vals index I. And then once we have the norm base, we can loop through it again. So for I comma val colon equals range of x vals, we'll say x vals index I equals val divided by norm base. Okay. And for now, we'll also say sum colon equals 0. And no, we actually have to say, sorry, var sum float 64. I'm only doing this to demonstrate what we've done. As we go through this, I want to say sum plus equals x vals. Okay. So now let's show what our, you know what, no, so he's making a new list called norm vals, and we should do that as well. So let's come over here and we'll say norm vals colon equals make, and this will be the same thing as this over here. We're just going to make an empty slice with the same length, except this time we should probably say with the length of x vals. Even though it's the same thing, let's just make it like that for consistency's sake. And then over here we'll say norm vals, norm vals index I. Yeah, things are good. Hold on, I want to get the chat up. Great. Okay, norm vals index I. And then we could say sum plus equals not x vals, but norm vals index I. And then I want to print the x vals, and I also want to print out the sum. The sum is just to show that everything is going to add up to 1. And so here we have, so he has the normalized exponential values, and these are them, and then the sum is 1. So that's pretty cool for him, that he got the sum to be exactly 1. I'm not sure if we're going to get that. Okay, so we get, this is, I'm printing out the x vals. I should be printing out the norm vals. Sorry, my bad. My bad. Okay, so we are getting, yeah, exactly very similar values that he's getting, and and it's adding up to 1. So, by the way, that is pretty much the softmax activation function. That is it. It's that simple. You're raising everything to the exponent. You're exponentiating everything. You're raising e to all of those values, and then you're dividing it by the norm base, and that normalizes everything so that it's between a range of 0 and 1. So you could get percentages. Now he's going to show how to do this in NumPy. Normally at this point I would show how to do it in our package, like the tensor package in Golang. I'm not going to do that in this episode. One, because it's hard to do, and two, because we don't really need to do it because I'll show you something that we could do instead, which is pretty cool. And three, no, one, because it's hard to do and so it's not worth our time. It's really not worth our time. That's the real reason. It's not worth our time. Because two, there's another way to do it which will be easier. And three, it's cool because now normally we're at a disadvantage, but in this case we'll actually be at an advantage. So for now we're going to follow along in raw Golang code because there is one more idea that we need to understand before we can continue. Yeah, there's one more idea that we need to understand. So let's do this. So he's just going to show exactly how to do this in NumPy. Sorry, hold on. Yeah, so all he needs to do is to, like, NumPy has a function, exp, which will raise it all, and then he's going to normalize it by the sum of all the values, and this will get him the appropriate things. Now he's going to show that when you try to do, like, batches, he actually runs into an error, an issue, because when he tries to get the sum to divide everything by that sum, he has a problem because it's getting the sum of all of these values. And he doesn't want the sum of all these values. He wants the sum of this to divide those values by that, and then he wants the sum of these to divide these values by that, and then he wants the sum of these to divide those values by that. And so he's going to show exactly how to do that in NumPy. There are a few values that he needs to pass in. Access equals 0. Keep dims is another value that he's going to have to pass in at some point. Yeah, right over here. Keep dims equals true. And then he's able to get it, and it works. So let's just quickly move things over to batches like he did, so that we can do some stuff. So over here, outputs, instead of being a one-dimensional situation, it's going to be a two-dimensional situation. And we're going to come over here and paste that in. And all of you square brackets need to become squiggly brackets. So hold on. Wait. And then all of you guys over here. Oh, so apparently I cannot just do that. I gotta select them one at a time. That's fine. And great. So now we have a two-dimensional outputs, and we're gonna have to figure out exactly how to code this, because now we need to. So for I comma val. So for I comma slice colon. I don't know. For I comma. I don't know, what should we call this? For I comma output. For I comma output colon equals the range of outputs, and then we have to basically just make a very similar for loop to what we had a second ago. So let's just do that, because it's going to be a multi-dimensional for loop. So for I comma val in range output. Yeah, so I don't think we need to do this. We could just do underscore over here. So I think this will get us our exponentiated values. So for now, let's just try and print that out. So over here, this also needs to be a list, and then this will be of length outputs, and then so over here we need the I, because we're gonna have to make exp vals index I equals make. This is just Golang stuff. We're making exponential values into a multi-dimensional slice, and so over here the slice will be the length of outputs, and each individual slice will be the length of outputs, or rather we could say the length of output, because that's this value over here, which is the slice. And then we could come over here and we could say exp vals index. So let's change this to a j, and that will be an I. So index I comma index I index j. Exp vals index I index j will equal the math.pow of, yeah, that's good, of e and val, and then norm base plus equals exp vals index I index j. Great. So now that should work. And let's print out the exp vals. We don't actually have to print them out because printing, well, let's print them out anyway. fmt.println exp vals. Great. And let's run this. I'm actually going to turn on the air conditioning, so give me a second. I don't like starting with the air conditioning on because it makes a weird noise, and I like to go for as long as possible without it on. Okay, so here are our exp vals, although they're in a very not nice format. So this is the first list, and this is the second list, and this is the third. The first slice, second slice, and third slice, and they're all exponentiated. exponentiated. So now we're going to normalize them. So the normalization will take place over here, and this will be a very similar getup. So the same kind of for loop situation over here, except now it's going to be over here, and we don't really need this anymore, or rather we need parts of it. So we need the sum. I want that. I still want that. Great. And I want the inside of this loop to go over here now. Okay. But now, yeah, so now we don't really need this. And now norm vals is going to be a two-dimensional slice with the length of exp vals, which is great. And then over here, very similar to how we did over here, we'll say, yeah, over here this is going to have to be norm vals index I. It's going to be a slice of the length of, and this is not going to be output, this is going to be exp val. Let's change this to exp vals. Nah, exp vals batch or something. And then over here we can say, actually no, I can't do that. For I comma, I don't know what to call this. Vals. Yeah, let's just call it vals instead of val. And then we could say the length of vals. For j comma val in range of vals. Norm vals index I index j equals val comma norm base. The norm base is still being created over here at every step as we had it before. That's good. And then sum plus equals norm vals index I index j. Great. And then fmt.println norm vals. And then, sums. Okay, so this is going to have to be sums, which is going to be a slice of float 64. So how about this? Sums colon equals make. So this is, now this is going to have to be like a make. It's gonna be a slice. Now it's going to have to be a slice with the length of exp vals, right? Yeah. Oh, this needs to be in the range of not outputs but exp vals over here. This is getting really confusing, which is why he likes doing it with NumPy, so you don't have to do all these like nested loops. That's why it's good. So now sums index I plus equals norm vals index I. Great. Okay, good. So now we could print out sums. So this should give us 3 normalized outputs. Additionally, we should see that the sum of them is all 1, which we're not seeing. Okay, so how many print statements do we have here to begin with? I don't want this. Thank you. And something is up. It does not look like all of them are adding up to 1, which is interesting, to say the very least. So let's find out why that is. Because norm base, we can't just be creating norm base as it is. Norm base also needs to be a slice. So we're going to have to do something like that. Norm base, it's going to be like that. And then we'll say norm base index I. And then over here, val index I as well. Yeah, that should work. Take a look at your code as well. I hope you're able to follow along. I hope we're not going too confusing. Most of this does not matter in the end, I'll be honest with you. But we're just, yeah, so these are the correct values. And as you can see, these are the normalized values for the first batch. These are basically batches. We're visualizing them as batches. This is the second batch, and this is the third batch. And then as you can see, each one of them adds up to 1, or very close to 1 at the very least. So good. Okay, that is how you set it up for batches. Just quick review, because I know I did that super quickly. We have these outputs, which is going to be the outputs from a given neural network as batches, because again we work in batches. That's why it's two-dimensional. So there's going to be like one output for one like this is going to correspond to one input. This is going to correspond to another input. This is going to correspond to another input. We have to exponentiate all of them. So again, this will be multidimensional because this is multidimensional, and it will have the same shape. So we create the first dimension of the shape over here, and then we create the second dimension of that shape over here. Now the norm base, the base that we divide them by, we're going to have several norm bases. We're going to have 3, because each one of these needs its own norm base, right? So that is going to have to be a slice with the length of exponential vowels, because the first dimension is returned by the length in Golang. And then we come over here and we set the exponential vowels index I, index j. We get I and j because we're looping through outputs and then output. We exponentiate the value, put it in there. The norm base at index I plus equals the exponential value at index I, index j, which is good. And so that's how we populate the exponential values slice. Then we have to get the norm values, so we have to normalize all the values. So that's going to be, again, a two-dimensional slice. We initialize it with the proper dimensions, just like we did for the exponential values, except in this case we're using exponential values as our base for the dimensions. And also I'm getting the sums. The sums is going to be similar to the norm base because I want to show that they all add up to 1. So that's also going to have to be a slice because we're going to have to have 3 of those values. So then we go into the for loop and we get I and we get the vowels, all the exponential values as we loop through exponential vowels. The norm vowels at index I is going to have to be made as a slice with the length of vowels so that we get our two-dimensional structure, as I've said before. And then we have to actually populate norm vowels. So norm vowels at index I, index j, we're getting j and we're getting value from looping through each vowels, each individual vowels collective or slice of values from exponential vowels. And then we divide val by norm base index I and we put that into, again, norm base index I. Why is it norm base index I? Because norm base is a one-dimensional slice and each index is corresponding to a given batch. So norm vowels at index I, index j equals the value divided by norm base at index I. And then we increment the sums so that we get that it all comes out to 1. And that is the SoftMax activation function for batches. Pretty complicated, right? It gets pretty intense. So there's one more thing. So he's doing exactly all of that, except he's doing it in NumPy, which we don't have to follow along with because that's not relevant for us. All I want to do is show. Yeah, this idea over here. So he's making the forward method for his activation class, which is okay. We're going to make it into a struct as well, but not right now. Okay, let's read this, because this is very important. Finally, we also included a subtraction. I don't know why it says included. It should really be include, because he didn't do it yet. But finally, we also need to include a subtraction of the largest of the inputs before we did the exponentiation. There are two main pervasive challenges with neural networks. There are two main issues with neural networks: dead neurons and very large numbers, referred to as exploding values. Dead neurons and enormous numbers can wreak havoc down the line and render a network useless over time. The exponential function used in SoftMax, so again, this is an exponential function over here that we use in SoftMax. It has a problem. The problem is that things get very big very quickly. As you can see, it only, oh my god, I did not mean to go that far up. Let's go down a little bit. Sorry. As you can see, it does not take very many values for things to be hundreds and hundreds of digits high. So that's not necessarily a problem, except computers have a problem at some point with big values. And if you exponentiate a number, say like 1,000, you're going to get an error. You can't do it. It's an overflow. It's infinity. Like to a computer, that is infinity. So we can't be doing that. Not okay. So what is our solution, though? Because sometimes we will have very big values. Sometimes a neural network will return very big values, and we don't want our SoftMax function to mess us up, right? There's a solution. There's a solution. The solution is, I'll show you. I'll just show you on Notepad, and we don't have to look at the book too much. The solution is, imagine we have an output, let's say 20, 30, and 1,000. So we've seen, or let's say 10,000. There shouldn't be a comma. we've seen that this is not good. This is problematic because it will overflow the computer, and we can't work with this. There's a solution. If we subtract each of these values by the maximum that they have, which in this case is 1,000, then we'll get something like this. What's 1,000 minus 20? I mean, what's 20 minus 1,000? Well, what's 1,000 minus 20? That is 10,000, I mean. You know, let's change this to 1,000. That way there are smaller numbers. So even 1,000 will make problems, right, as we see over here. Overflow. So what is 1,000 minus 20? Well, that's 980, so this would be negative 980. Comma, what's 1,000 minus 30? Well, that is 970, so this will be negative 970. And 1,000 minus 1,000 is 0. Okay, so now, why is this helpful? Well, I'll tell you. If we now, instead of exponentiating these, which would cause an error, if we exponentiate these values, we'll constrict it within the range of 1 and negative infinity. Now, the benefit is, no matter how small your numbers get, no matter how far negative they go, they are approaching 0. They'll get closer and closer to 0. So that's not really a problem. If you have a value of 0, that's going to be 1. So that's just going to, like, e to the 0 is 1. Anything to the 0 is 1. So now we've constricted it. Instead of having a range between 0 and infinity, now it has a range between 0 and 1. Which is good, because we don't want a range of 0 to infinity, because infinity is very big. And we can't be dealing with values that large. We can't even deal with values at 1,000. So if we subtract everything by the maximum, we dodge that error, and you'll still, since it's proportional, since everything is keeping its proportions, we'll still get the exact same percentage values back. At the end of doing the whole SoftMax situation, we'll still get the same percentage values back. Okay, so that's our solution. What we're going to do is, let's go over here. What we are going to do, quite simply, so as you can see, he's showing if you exponentiate something to negative infinity, it's 0, and if you exponentiate to 0, it's 1. So now it's a range between 0 and 1, which is much better. Okay, so let's show this exactly. Let's show exactly how this would look in code. So this is going to happen. This subtraction step is going to happen before we even exponentiate things. So it's going to happen right over here. So let's make some comments. Subtract to avoid overflow. That's going to happen over there. Then we exponentiate vals. Why are we doing that? We exponentiate to remove negatives, because again we don't want negative values in our proportional output. We just want percentage values. And then we, over here, normalize to get percentage confidence. We want to get the confidence of our neural network. Excuse me. Great. So that is good. So now we have those comments. Let's subtract. Let's do the subtraction step. So for I comma vals colon equals the range of outputs. So now we have to get the minimum of this. So is there a way to get a minimum value of vals? Not really. I mean, I guess we could. Yeah, let's do over here. Min colon equals 0. In fact, no, I have to really do, yeah. Var min float 64. For j comma val colon equals, or actually no, min should by default just colon equal vals index 0. It should just equal the 0th index of vals. Not 0, because you may have something that is, you may not have any values that are bigger than 0, but I don't know. You don't initialize it to 0 when you're finding the minimum. You always initialize it to either a random value in the list that you're searching in, or you initialize it to the first value in the list that you're searching in. So for j comma val colon equals range vals. So again, this is just a simple nested loop. We're going through the outputs, and we need to get the minimum. So if val is less than the min, then min equals the val. And I guess we don't need I guess we don't need j in this loop. So now that we have the min, so this is getting the min. Getting the min. Now that we have the min, we have to actually apply the min. So let's do a very similar loop over here. And this one we do need the I. And yeah, so we say outputs index I index j. I'm sorry, this is supposed to be a j. Equals the val minus the min. Right? So this gets the minimum in our given output sample, and now over here we have to apply it. So now we've done that. And you'll see that everything runs as before, except we've avoided the error that could come from exploding values. And in fact, this is actually great because now everything is 1. So apparently we've gotten even more precise, which is pretty cool. So that's nice. And these are, you'll see that these are all, if not exactly the same values, basically exactly the same values as they were before. In fact, we could see because we didn't actually remove that thing. So let's see. Let's check out this. These are the values now with our subtraction, and this was it before subtraction, I think. No, it's not. Something's weird. Something's weird with the formatting. That's okay. That's okay. I guess we can't see. But one thing that we can do, or actually no, we could see. Let's check something out. If we comment out everything that we did over here, we'll get it exactly how it was before we did the subtraction step. And as you can see, this is basically the same value as this, and all of them follow the same basic value trend, and you can check it for yourself. But the reason why I wanted to comment that out is because I want to show you that before, say one of these values was like 10,000, like that, this will throw an error. We'll get an overflow error, and things will break. See, yeah, it doesn't even throw the error, it just doesn't even tell us because it got an infinity value. And now we have, yeah, this is problematic. So if we do this, if we have this subtraction step over here, we can completely dodge that error, which is desirable, right? So let's try it now. That's not good. Okay, something went wrong. Apparently, it's still not working. Okay, so let's figure this out. Let's comment all of this, and let's just inspect our outputs. After we do the subtraction step, let's say fmt.println outputs. That's all I want to do. Let's check it out. See what our outputs look like. None of them should be... So that's weird. I'm sorry. We don't want the minimum. We want the maximum. I don't know what I'm doing. I don't know what I'm talking about. We want the maximum value, not the minimum value. We want the biggest value that they have. Sorry. Wow, that is quite a goof. I did it such a... Wow, that's quite a... I goofed up. Okay, let's try that again. Still not... because I changed the value name, but I didn't check the actual code. I didn't change the actual code, so now it should work. Okay. Very good. So this is exactly what we're looking for. And, okay, so let's uncomment everything else and try it again, and you'll see that it works. Probably, I hope. Let's just see that it works. There's a problem. What's the problem? What's the error? There's an error. Where's the error? The error's over here. This is supposed to be commented. And isn't there another one? No. Okay. Oh, and we need math. We need to import math again. Sorry. Math got unimported. Math. Great. Okay, let's try that again. And it's working. Excellent. This part isn't working as it was before because we removed the value and we've made it crazy high, and so yeah, we made this value crazy high compared to the others. But what was it before? Let's just check what was it before, so that we could move it back to being what it was before. It was this. It was 2.385. 2.385. Awesome. Let's try that again. And now we get all the same values as they were before, and we've avoided the exploding problem that we would have encountered. So there we go. This is the SoftMax activation function as seen in raw Golang. I hope it makes sense. Now let's go to where he's up to. So he fixed that, and great. So he has the SoftMax activation class. So let's make something similar. Let's come over here to our machine learning package. We'll make a new file. Oh no, we don't need to make a new file. We'll just go to activations.go, where we have all of our activation functions, and we're going to make a new situation. So SoftMax, and over here this is ReLU. Okay. Type. What's the format? Activation SoftMax. Okay. Activation SoftMax. Nope, that's not. It's a struct. Okay, and this will have a output, which will be of type t.tensor. Because again, we're going to move things over to the tensor situation that we had before. And I'll show you exactly how to do this. So this is going to be very silly. Func, let's say s star activation SoftMax, and this will be forward, and this will take in inputs, which will be of type t.tensor, and this will spit out. Oh, not spit out. This will also need to take in the axis, which will be of type int. Okay. So now this is going to be a little bit annoying, but remember how I said we didn't need to learn how to do it in our tensor package? It's because we could do something like this. Output, let's say output, comma error, colon equals t dot soft. Oh no, wait, hold on. Soft. No, there's a straight up SoftMax, isn't there? What's going on here? I remember there was a straight up SoftMax function. Hold on. Output colon equals t dot softmax. What? Why does it say log softmax? I want just straight up softmax. I'm telling you, there was I was checking it out in the beginning of the video before I started recording. There was a softmax ability for Orig.org/tensor. There was a softmax function that we could use. Hold on. t.soft. Someone is playing tricks. I'm telling you, someone is playing tricks on me. Let's check something out. Let's go to the documentation real quick. Tensor Oregonia.org/tensor, and let's search for SoftMax. Log SoftMax B. Here. What is this? That's the SCD engine. SoftMax. Oh, these are all here. Func SoftMax. Excuse me. Hey, did I just misspell it? Is that the problem? Max? No. Func SoftMax. It's right here. It's literally right here. What's going on here? t.softmax. You're telling... Oh, there you go. Okay, so it found it. Okay, for some reason the autocomplete wasn't showing it. That's weird. Okay, fine. Great. So the softmax takes in, and it's also going to return an error, by the way. So softmax, and then this takes in a tensor inputs, and it also takes in an axis, which we pass in over here. And there you go. So it returns an error. So let's say handle error. And if there is no error, then we say s.output equals output. The reason why we had to do this in several lines is because we have to handle for the error first. So there you go. I hope you understand how the softmax activation function works. If you don't, rewatch the video and figure it out, because it is really a cool function, and it's really fun, and it's really cool math, and it's very useful math, and so it's cool. But the point is, our library has a softmax function, so we don't need to do it, which I guess is kind of cheating, but whatever. That's fine. So let us show exactly how this looks in our code using our actual sample. So we could get rid of all of this code. All of this raw Golang code was just to show exactly how it works. I hope you understood. So that's all gone. And now let's bring back our dense one and activation one. And we could remove this. And we don't really need math anymore. And okay, so what does he have right now? SoftMax. So he's just showing exactly how this works. So let's, and then he's gonna. Okay, so this is what I want to see. So this is the data. We have the data in our separate file over here at data.go. Go check out a previous video to see how we got that if you don't know. So he's making a dense one, an activation one, a dense 2, an activation 2, and he's forwarding through all of it, and then he's showing what the output is. But the activation 2, in this case, is SoftMax, which is interesting. Okay, so let's do this. So let's make our second layer. Dense 2 is going to be ml.newLayerDense, and then over here we can make our activation 2. Make the first layer, and I'm going to count the activation functions in the layer. So make the second layer. So here we go. Activation 2 colon equals ml dot new. We have to make a new. Here, let's do something similar over here. We have to make a new activation softmax function. So new activation softmax, and this is going to return. This is going to return a activation softmax, and this will return activation softmax, and the output is going to be set up to a default tensor, which is good. Okay, so that's good. So now we say new activation softmax. Excellent. And then over here we can do dense1.forward, activation1.forward, the dense1.output, and then we could say dense2.forward, and this will be activation1.output, and then we could say activation2.forward, and this will be dense2 output, and this one also takes in an axis, which is important to remember. So we don't want it to do softmax over the entire batch, right? We only want it to be in the first dimension. As you see over here, he has to pass in the axis of 1, because if you pass in an axis of 0, since this is a multi-dimensional thing, it will treat all of the samples as one thing, and we don't want that. We want it to treat it as each sample in the batch as its own separate situation. So we need to pass in an axis of 1, essentially, because we're working on the first axis, which is the second dimension. It's a whole thing. Okay. And now let's print out activation2.output, and you see they're all 0.33, because in the beginning, since everything is random, all these add up to 1, and the AI should be, it should just be doing things at random. It shouldn't know anything. Hey programmer, JavaScript. Nice to see you, man. Okay, so sorry, lost my train of thought. Great, so we should be expecting everything to have a value of 0.33333. If it doesn't, I'm going to be very sad, and we're going to have to do some heavy debugging. So let's just check out activation2.output. Oh, please work. Oh, please work. I'll be so happy if you work. Work. Just work on the first try. Just work on the first try once for me. Okay. For some reason, it's not working. Probably because I didn't make my dense 2 layer the same way he did. So how did he make his dense 2 layer? It's a shape of 3, 3. So I made it of a shape of 3, 2, which we don't want. How did he make his first layer? 2, 3. Excellent. So now it should work. Because as you see, it was 0.5, and this is also 0.5. So it was working. It's just not exactly the way he had it. Okay, and it's working. Ta-da! It's working! So as you can see, since the AI is initialized with random values, it's basically picking which class it thinks a given input should be in at random, at complete random. And yeah, so since there are 3 classes that it's working with, it's just picking it at random. It doesn't really know. And only one of them will be slightly more confident than the other. So there you go, ladies and gentlemen. I believe that is the end of chapter 4, which is all about activation functions. Personally, I think that this is one of the most important chapters in the book. Here's all his full code up to this point, which is cool. So yeah, I think that this is one of the most important chapters in the entire book, other than chapter 5. Chapter 5 is also incredibly important. Calculating network error with loss, I think, is crucial. And also, the coming chapters are also all very important. But I think activation functions are something that a lot of people don't understand. They just say, oh, we just use activation value. What does it do? Why do we use it? We have no idea. But so now you know the math behind it. Now you know how it works, which is excellent. All of our code up to this point, let's clean up our code a little bit because we have a lot of comments and stuff. So let's get rid of that. All of our code up to this point does not fit into one file, like his does so cleanly because he's in Python. But we have this main file, which has all of our layers and stuff. And then we have this machine learning package, which has, you know, the activations and the add bias and the dense layer struct, obviously, which is a pretty cool struct with the forward method that we did in another video. Then we have the plotting file, which we use to plot our graph. And I'm not sure what this is. Oh, this is something that I made in the beginning of the tutorial series that we never ended up using. Okay, so we don't really need that. Okay, great. So that is the end of chapter 4, all about activation functions. Hope you learned something. Hope you enjoyed. Leave a comment with any questions. Check out previous videos for more in-depth, not more in-depth, but to check out the other tutorials and follow along with this incredible journey that we're having, which I'm having a blast doing. Obviously, not obviously. Honestly, I did not expect to have 9 videos before we even got to chapter 5. I expected to have 4 videos before we got to chapter 5, each one of them on their own chapter, but things ended up being much longer than I thought they would be. So this is the situation we're in. Hope you guys enjoyed. I will see you next time. Bye. I'm going to end the stream now.